So let's talk a little bit about how pollutants move through groundwater. The most obvious way is that this is the movement of contaminants in groundwater. So the most obvious way is that they just get carried along. One possibility is they just get carried along with the moving water. This is a process referred to as advection. This is like a stick floating on a stream, right? It's just a passive occupant of the water of the river, and it just gets floated along. As this happens, however, the contaminants will often undergo what's called dispersion. And this can be, well, before I describe how it can be, let's talk about what it is. So imagine that we have a series of pores, or let's say sediments here, grains of sand in an aquifer. And we've got two molecules of contaminant, one of them in blue and one of them in orange, and they're right next to each other, and they're both moving along with the water, which is moving in this direction, right? Through the groundwater is moving through the sediments. Well, you can imagine that one of them takes, just by random luck, takes a very, very linear route through those pores, and still traveling at the average speed at which the groundwater is flowing. But because it took a pretty linear path, it's going to move quickly from the start to the end. You could also imagine, though, that we have, again, just by random luck, this molecule still moving at the mean average speed, but because it takes a much more circuitous route, it's going to get through this batch of sand much later than the blue one did. The orange one is going to arrive much later. So as a result, what we end up with are plumes. Plume is the sort of the name for the area of contamination. Contamination in groundwater. So you can imagine that if you had, let's say, let's look down from space here. Here's a map, and there was some sort of spill that happened, at midnight of one day, that we wouldn't, and so somebody, let's say, accidentally or on purpose poured a barrel full of some sort of oil or solvent down a well, right? So the spill was a jolt of a small amount of material. It started and lasted for a very short period of time. What would happen? Well, if there was no dispersion, what you might expect to see is that 12 hours later, the entirety of the oil or whatever had been spilled down the well. Let's say water is moving this way, groundwater flow is moving this way, and 24 hours later, it would be here, and 36 hours later, it would be here. And of course, that's not what's going to happen. Instead, it's because of dispersion. It's going to be the plume is going to be stretched out, and it's going to look maybe more like this. It's going to have a series of contours where the plume maybe looks like this. So the low concentrations are on the outside and the high concentrations are on the inside. And the reason it's been stretched out in the direction the groundwater is flowing is because of processes like this. Random variability of molecules flowing along shorter or longer flow paths. The same thing can happen. This is, by the way, is referred to as longitudinal dispersion. Longitudinal dispersion. We can also get transverse dispersion, however. Transverse dispersion. Right, this is longitudinal. Transverse is the opposite. It's this. It's the fact that over time, this plume is not only stretching out sort of east-west, it's also going to be stretching out north-south. And so this plume groundwater flows this way. Is not only going to be getting stretched out longer, it's going to be getting stretched out wider. This is transverse dispersion. This is longitudinal dispersion. Right? And so if we were to contour this, we might see something that looks like after some amount of time, who knows, maybe the plume looks something like that. Okay. Another way that water can move is through, or excuse me, that contaminants can move is through diffusion. Diffusion is independent of groundwater flow. Diffusion happens even if the water is perfectly still, and it's driven by the motion of the molecules and concentration gradients. Stuff wants to diffuse in liquids, in fluids. Stuff wants to diffuse from where it's more concentrated to where it's less concentrated. And the equation that we use to, one equation that we use to describe that is Fick's law, Fick's first law, which will have a very, very familiar look to it. And it's written as F equals negative d dc dx. And what this means is that the mass flux, in other words, the movement, the mass flux is the movement of contaminants in solution, is equal to the diffusion coefficient, which is the ability of the material of the fluid or whatever it is to allow diffusion to occur, times the concentration gradient. What is the change in concentration between 2 points separated by some distance? And this, of course, looks a lot like Darcy's law. And you can write the same equation for the flow of heat, which would be something like Q equals negative K dt dx. So they all have the same basic relationship, that what drives them, what causes things to move at all, is a difference in value, like a difference in concentration or a difference in hydraulic head or a difference in temperature over some distance. And what determines how fast the material or the heat or the water or whatever it is can move from point A to point B is this innate property of what it's moving through. The aquifer has a hydraulic conductivity. The insulation in your wall has a thermal conductivity, and the aquifer has some sort of diffusion coefficient. Okay, so Diffusion in general is quite slow. Diffusion is quite slow. And so, except in areas where groundwater is moving very, very, very slowly, diffusion often doesn't play a huge role. All right, so let's talk about ways that we're going to remediate or clean up remediation of groundwater pollution. There are lots of things to consider here when we're thinking about how to clean up a spill. And the first thing you need to think about, right, is the type of pollution. So imagine, for example, something like this. Imagine we have a house, and it's sitting. It has a basement. And it's sitting on some ground that has water table down here. And somewhere over here, let's say the water's moving this direction. Somewhere over here, there is a leaking underground storage tank. And that leaking underground storage tank has been losing gasoline for decades. And so what's going to happen? Well, this gasoline is going to migrate through the unsaturated zone. This is the saturated zone right below the water table. It's going to migrate down. Some of that gasoline is going to get caught up in the, is going to remain in the pore spaces of the unsaturated zone. Some of it's going to continue down. When it gets down here to the water table, it's going to float. So we're going to have a plume of gasoline. And that gasoline is going to advect along with the general direction of the groundwater. So it's going to be carried along like this. And as it does, because gasoline is so volatile, it goes from the liquid phase to the vapor phase so easily, you're going to be losing gasoline, or I should say, maybe more importantly, you're going to be building high concentrations of gasoline vapor in the areas right above the water table, right? So we can envision a scenario here where some of these vapors actually make their way up into the basement of this overlying house, come in contact with build up over time, come in contact with the pilot light for the furnace, cause a fire, cause an explosion. Right? So even though this is a leaky underground storage tank a long way away, it's actually able to impact potentially what's happening in this house. So lots of things to factor in here, right? We have L-naples in the gasoline. We've got the vapor phase. We could also envision a scenario maybe where you have something, this would be a little bit fantastical, but we've got a land surface that looks like this. We have let's say, a bunch of soil up here. We've got bedrock that's angled for whatever reason down like this. And we have a water table that is moving through here. Okay, so you have some sort of, and the water, let's say, is moving that direction, groundwater flow. We have some sort of spill here of L-naples and D-naples combined in some nasty mixture. And the L-naples and the D-naples infiltrate through the overlying soil. They hit the water, and the L-naples are not soluble, but they're going to float, so they're going to be transported, going to be advected along with the water. The DNAPLs, however, are insoluble but heavier than water, so they're going to continue down. Maybe they hit I don't know, maybe this is some sort of shale layer or something that's got a very low hydraulic conductivity. And so the DNAPLs then are going to begin to migrate slowly, falling down the edge of the shale in the opposite direction that the LNAPLs were transported by the groundwater. Okay, that's one possibility. And then, of course, the third possibility is that you have something like, my computer tightened up, that you have something like this, where you have a water table here, and the water is, let's say, moving in this direction, groundwater flow, and you have some sort of contamination, say, from a pesticide, which is water soluble. And as this stuff comes down, it doesn't float, but it dissolves and is going to and form a plume that is advecting and dispersing, not only along with the direction that the groundwater is flowing, but it's also good, since it's dissolvable, is going to be moving further down into the aquifer itself. So lots and lots of problems here. And the first thing we need to do, right, if we're brought in to characterize a site where a spill has taken place, is we need to figure out what to do when brought to a new spill site. Actually, I think what I'll do is I'll hold off on that, and we'll discuss it in groups this afternoon. So I'll come back to that. Let's see, is there anything else? Yeah, I guess I can skip over that and just talk about some ways that spills are remediated, that they're cleaned up. So one is that if it's shallow, if the spill is shallow and in loose sediment, if the spill is shallow and in loose sediment, you can excavate. So you literally bring in a backhoe. Let's say you have something like in Iowa, let's say you've got glacial till, which, as you may recall, has a very low hydraulic conductivity. And you've got some sort of, I don't know, leaky underground storage tank there, right? And you've got this contaminated area all around it, but the water table is down here. And if you determine that this stuff maybe hasn't reached all the way to the water table, or even if it has, let's say you find the spill looks like this. Okay, that's the full edge of the plume. There's the plume. What you can do is you come in and you excavate everything. You pull out the tank and you dig out all of the sediment in that box, everything that's contaminated, and you haul it away. And what do you do with it? Well, depending on what the contaminants are, cleanup can be as simple as incineration. If it's gasoline, which is what's obviously gasoline or oil, which is most common in these underground storage tanks because they were fuels, you put them in big burners, you put the dirt in the big burners, you heat it up, and the petrochemicals, the oil and the gasoline, just burn off, and you vent those to the atmosphere. And now you've got essentially more or less clean dirt, which you could bring back in and put it back in the same spot, or landfill, or take somewhere else. This is going to be expensive, but obviously it's a quick and finite solution. What if you have contaminated groundwater? Contaminated groundwater. Well, if it's contaminated groundwater, you have a couple of different possibilities. One is pump and treat. in which case you would literally sink a well into, let's say you have a plume of stuff that's moving this way. You put a well into it and you pump it out, and when it's extracted, depending on the size of these things, you either have an on-site or an off-site treatment system. That extracts the contaminants. In some cases, the water that's been treated, which may still have some small amount of contaminants in it, is actually brought over and re-injected back upstream of the plume so that it then gets recycled in with the plume and it undergoes multiple courses of treatment. So you basically have a sort of a capture zone here. In some cases, if you had, let's say, I don't know, a very sensitive, like a big municipal well here, supplying lots and lots of people, and you have this very dangerous plume making its way here, you might not only want to put in a pump and treat system. In some cases, what's done is, these are sort of extreme measures, but they actually will put in complete hydrodynamic barriers. So they'll shove big steel plates or pour concrete or something down in there. And the idea is that any water that's still contaminated that makes its way past the pump runs into this barrier and can't get beyond to impact the municipal well. Alternative methods are to, in some cases, it's just hydrodynamic isolation. So this is not a long-term fix, but does stop the problem. Remember that we're going to look down from space here now. This is a map view. If water, let's say, is flowing, groundwater flows left to right, and you have some sort of spill here. Here's our site of our spill. Right, so the contaminant's moving that direction. What you can do is you could put in a pumping well, right here, pumping well, and start pumping the water out. And as you pump the water out, you're going to create, as you recall, a cone of depression, so that the water table is going to be depressed. You can draw it kind of in concentric circles here. Right? Remember, the cone of depression is going down like this. So as a result, the water is going to be flowing in from all sides, right? And the spill and all the plume here, it's going to reverse its direction. So the water in general is moving this way, but in the area that's captured by this cone of depression, the water is going to be moving the opposite way. It's going to be pulled in here. So you could conceivably pull this water in and then re-inject it back into the ground at different wells here. And the water basically is going to move out and come back in, move on the surface, be pumped back in, come back. And so it's caught in this continual loop. And so while you're not actually cleaning the water, you're not allowing the water that's been contaminated to move beyond the cone of depression. So it's cone of depression. The cone of depression captures the plume. And you can do that even if you're not cleaning the water. In some cases, bioremediation has been used. Wherein you inject bacteria into the subsurface. And they're bacteria that are the type that that eat petrochemicals or eat organic compounds, right? So they break down the organic compounds that you're worried about. In some cases, these are anaerobic, meaning they don't require a lot of oxygen. Typically, however, they do require oxygen, and so oxygen is injected along with them to make sure that not only do they have plenty of food to eat, but they've got plenty of oxygen as well. For things like the vapor, this is a real problem. So we talked about underground storage tanks before, and you get this gasoline or whatever it is that's soaking down, right? Well, if we zoom in on that really closely, right? So here's a bunch of grains of sediment that are in the ground, grains of sand, right? And the gasoline, whatever it is often sort of hanging out in these pores, right? So what's done to clean this up in some cases, if you pull the leaky underground storage tank out, but you still have all this gasoline that you can't get rid of and it's too deep to excavate. So what's done is they will put these pumping wells in there, but you're not pumping water, you're pumping air. You basically create a big vacuum. And the idea is that you want to suck the gasoline out. Now, because this is the unsaturated zone, because it's not below the water table, you're not going to be able to get the gasoline as a liquid phase. But what you do is by creating a vacuum, the gasoline wants to volatilize, right? The gas volatilizes. Volatilizes, I don't know how to spell volatilizes. Means it goes from the liquid to the vapor. And the vapor phase then gets pumped out and vented into the air, right? There's a problem with that, though. And that is that when you look at the concentration of, say, gasoline in the vapor that you're extracting, so if you were to be measuring this air that gets pumped out, measure how much gasoline is in it per liter of air. Measure the amount of, and then measure that versus time of pumping. So you start pumping, and what you get, of course, at the very beginning is a very high concentration of gasoline vapor in the air that you're pumping out. And this will sort of exponentially decline over time, and it'll go way down. Okay, so you think, that's great. We've done all the pumping we need to do. Let's turn the system off. And you turn it off, and you go back a few days later, and you turn it on again, and the amount of gasoline in the vapor is really, really high. And you pump it down over time, you turn it off. So what's happening basically is that this gasoline is clinging to the edges of these grains, and it doesn't want to come off. And so in order to get that last bit of gasoline out of these things, it's not a simple following of this exponential decay. You need to pump and pump and pump and pump and pump and pump. So to draw it maybe more realistically, it's going to look sort of like this. And you're going to be gas in the vapor. Time is way out in many cases to years before the concentration of gasoline is completely removed using this technique, which is called vapor extraction. So it's a long and, quite frankly, noisy approach, but it can work. Okay, what else? I think that's all we'll talk about here.